So welcome to my channel on technology space with machine learning and artificial intelligence. So the today's topic is covariance and correlation in digital twin. So this is the part one of a two-part series, and this is also part of the playlist of digitalization. So let's move on to the main content of this presentation. So let's try to answer the question of why such statistical properties are important in data science. In one of my videos, I have discussed the topic of extreme data. I would place the link to that video also in the description of this video. So if you're interested, you can go through with that. In that discussion, we have mentioned these extreme data sets can be distributed in a large or high dimensional space. And then these data can have various data clusters having different shapes and structures in these data clusters. So therefore, at some point, we are interested in learning about these data clusters. So these statistical properties could guide us to learn the features in these extreme data sets. So the feature learning process is not a straightforward. We often use the machine learning algorithms to learn these features in this data set. So there is statistical properties eventually can guide these machine learning algorithms to understand this extreme data. So therefore this approach also can be classified as a supervised approach because you are guiding these algorithms to learn these digital twin type of models. And so the statistical properties we're going to discuss throughout this discussion would be mean variance, covariance, and correlations between different parameters in a data set. So I think that could build upon that good foundations to understand the actual digital twin models in the future. So let's try to define the first statistical property in this discussion, which is mean. The mean is represented by mu x that represent the average value in a data cluster. So if you're considering a data cluster with n number of values and this data cluster values are represented by x1 to xn, so the mean value would be summing up all the values from x1 to xn and then divided by the number of values which is n in this situation. So if you're looking for a simple example, here I'm introducing a data cluster with value from 1 to 5. So the mean value of this data cluster would be adding all these 5 numbers, which is 1, 2, 3, 4, 5, and then divided by the number of values in this cluster, which is 5. So then you end up with the result of 3. So these data points in this figure I have represented by blue dots. As you can see, it's varying from 1 to 5. And then the mean value I am representing by a red dot, which is the average value of 3. So as you can see, the mean value always would be in the center of this data cluster, since that is the average value. So let's try to define the second statistical property in this discussion, which is variance. Variance measure the average squared deviation from the mean. So the variance is denoted by sigma x in that case. So when you think about the equation for that variance would be, let's consider a data cluster with n number of values and then these values represented by x1 to xn. So it's a variance sigma x, also denoted as a VAR x, that means the variance of that parameter, is equal to you pick each data point and then you subtract mean value from that data point and then make a squared version of that. So if you done that for n number of data points, then you have n number of squared values. Then you add up these n number of squared values and then you divide it by the number of data point, which is n. So this formula we can often use for the larger data sets. But when you come to a smaller data set, this formula has a slight deviation. Instead of dividing the number of data points n, you divide it by n minus 1. So here I am representing a simple example with respect to the variance. So here I am considering a same data cluster with values from 1 to 5. And as you know, we calculated its mean value in the previous step as a mu x equal to 3. So then the variance would be you subtract 3 from each data point and then you make a squared of that and then you add up these values. And then you had a 5 data values. Since this is a smaller data set, we do the n minus 1 formula. So that way you subtract 5 minus 1, you end up with 4. So then the results would be 10 divided by 4, which is equal to 2.5. So we have calculated the variance for this data cluster as 2.5. So in this figure, I'm representing the 5 data points in this data cluster as well as its mean value. Even though I'm not representing the variance value in this data cluster in this figure, it's kind of representation of how spread these values throughout its data space. So let's try to define the third statistical property in this discussion, which is a standard deviation, generally denoted by the lowercase sigma x. So since we have defined the variance, it would be easier for us to define the standard deviation. So the standard deviation is the square root of the variance. So in this formula, I am representing that lowercase sigma x equal to the square root of the uppercase sigma x, also the square root of the variance in that data set. So here I'm considering the same data cluster with the mu x mean value equal to 0 and the variance equal to 2.5. So the standard deviation is the square root of the 2.5, which is give you 1.5811. In general, we would like to represent the standard deviation in a data set. So in this figure, I am representing the 5 data points as well as the mean value in the red dot. And then I have 2 green dots. This is representing the standard deviation of this data cluster. You should remember when you are defining the standard deviation, we always define that with respect to the mean value. So as you can see, my first green dot from the left is denoted by mu x minus sigma x. So that means the mean value minus the standard deviation represent that first green dot. So the green dot from the right represent mu x plus the sigma x. That means the mean value plus the standard deviation. So like that, when you're representing the standard deviation, always say look into the mean value and then would say how much this data been spread from the mean value with respect to the standard deviation, which give you a measure of that spreading condition of that data cluster. So let's define the next statistical property, which is covariance. So covariance is somewhat similar to the variance, but when you come to variance, we define with respect to a single parameter. But the covariance should be defined with respect to 2 or more parameters. So let's consider a data cluster which consists of the parameter x and y. So each parameter will have n number of data points corresponding to the respective parameter itself. So if we combine the corresponding x and y values, then you would end up with a data instance. So there would be n number of data instances for this data cluster. So the covariance measure how much 2 parameters spread together in a linear relationship, but you can calculate this value by in the following equation. So the covariance denoted by uppercase sigma xy, which is also equal to COV xy, that means the covariance of the 2 parameters, is equal to this equation, which is representing a situation where you pick each instant of the data and then you subtract the mean value of each parameter and then you multiply those 2 values. So similarly, you do that for the whole data set, for the whole data instance, and then you end up with n number of values. Then you sum up all these n number of values and then you divide that summation by the number of data points. This is generally for a larger data set, but if you're dealing with a smaller data set, you divide it by the n minus 1. So let's try to do a simple covariance calculation. Here I'm considering a data cluster with 2 parameters x and y. X consists of 5 data points, namely 1, 2, 3, 4, 5, with the mean value of 3 and the standard deviation of 1.5811. And the parameter y consists of also 5 data points with 2, 4, 6, 8, 10, with the mean value of 6 and the standard deviation of 3.1622. So let's create the data instant for that data set by combining the corresponding x and y values. For example, the first data instant consists of the x value of 1 and then the y value of 2. So let's calculate the covariance for this data cluster or the two parameters. So the sigma xy is equal to, first consider the first data instant and then subtract the corresponding mean values from both x and y values and then the outcome multiplied by each other. So like that you do it for the 5 data instant in this situation and then you add up to get the final number. And then you divide it by the number of data points in this case. Even though it is 5, we use the 5 minus 1 because this is, since this is a smaller data set. Eventually you end up with the final value of 5.0. So the corresponding covariance value for this data cluster would be 5. So let's try to display the information that was presented in this data cluster. So it had the 5 data instance. So this 5 data instance been represented in this figure as blue dots. So as you can see, there are 5 data points corresponding to this 5 data instance. And then there's a 2 mean values which is related to the x and y. The x mean value is the 3, the y mean value is the 6. That's also denoted in the same figure as the red dot. And then we also consider the standard deviation for the both x and y parameters, and the both standard deviation corresponding to the same data cluster also denoted in this figure. So let's try to define the next statistical property, which is correlation. So let's consider the same data cluster which has n number of data instant with two parameters x and y. X is having the mean value of mu x and the standard deviation of sigma x. Y is having the mean value of mu y and the standard deviation of sigma y. And these two parameters are having the covariance of sigma xy. So the correlation measures the strength and the direction of these two parameters, how it's varying together as a linear relationship. So generally this correlation can be defined for 2 or more parameters. And then this correlation value should always be in between +1 and the -1. So the equation for this correlation calculation would be rho xy equal to this CORR xy, that representing the correlation between two parameters, equal to the covariance value of the x and y divided by the standard deviation of the x and y. So that is the main equation that is related to the calculation of the correlation. So let's try to do a simple calculation on that by considering the previous data cluster with x and y values having the same mu and the standard deviation values. But this case you also have that the covariance value, which is related to the two parameters of x and y, which is equal to 5. So the rho xy equal to 5 divided by 1.5811 times 3.1622, and it is approximately equal to 1. So that means these two parameters are having a really good correlation. In the future, when you're considering various data sets, I would utilize these vectors to represent the covariance direction as well as the correlation relationships in these parameters in the future. So that's the end of my presentation, and then I have also created a video on a Python exercise that is related to this video, and you can also download the Python codes. So the more information on that exercise and the Python codes, I would put it into the description of this video. So hopefully you have enjoyed this video, and so if you are still interested, please stick around. Thank you.